Hi, my name is Peggy Hentz, and I'm from Red Creek Wildlife Center. I'd like to thank you for joining me in this section on medical math for the Wildlife Rehabilitator. Before we begin, there is a 30-page handout that accompanies this course. Make sure that you have it. Also make sure you have on hand a pencil or pen, paper, and a calculator for doing the calculations. Let's get started. In wildlife rehabilitation, basic mathematical calculations are needed when calculating drug dosages, fluid therapy, feeding amounts, caloric intake, and when evaluating diets. The wildlife rehabilitator also needs to be proficient in the use of several instruments of measure, such as a scale and syringes. Also, an understanding of the metric system and the ability to convert to and from the U.S. customary units is essential to proficiency in medical math. I'd like to say something up front. This class is meant to go from the very simple to the complex. For those who have some background, please be patient with the simple stuff. For those who really panic over math, I'm hoping by the end that you'll be much more confident. When I was first introduced to medical math, I tried to understand the concepts of lengthy drug dosage calculations. A simple question to determine how much of a medication should be given to an animal could be as complicated as this. There was no way I was going to memorize that formula. There had to be a simpler way, and there is. A math problem is simply a story in steps, and it can be broken down into several small, easily solved problems. This equation is the simplest, and mastering just this one simple equation will be all you need to solve complex problems. This is not a fraction, but a way to write a ratio. It can also be written many different ways. I like this one because we know 1 doesn't equal 5. Or does it? Now it makes more sense. We know 1/4 equals 5 nickels. They both equal 25 cents. So let's look at our original problem, and it would look like this. The fraction-looking ratio now makes sense. So how many nickels do you need to equal 2/4? 10 is correct. You just did a 2-step calculation in your head. You have all the skills you need to do this math. And here's the original problem, but this time, to make it more understandable, we are going to label them. Labeling is critical. It keeps you from making mistakes. Get in the habit of labeling from the very start. This will be important later for drug dosing when we start working with milligrams and milliliters. Like items always go on the same level, such as we have the quarters on the top and the nickels on the bottom. Now we know the answer to this is 10, but how did we get there? This is called ratio or comparative math. If you learn this one mathematical concept, you will be able to solve almost all of your problems. The magic of this is that diagonal numbers multiplied together will get the same answer. So these two numbers multiplied together will always equal these two numbers multiplied together. But how do we mathematically discover the missing number? You multiply the diagonal that has two numbers and divide the answer by the odd number. And it works with everything. Grab your calculator and try another one. Did you get it right? There are practice problems throughout your manual. The answers are in the back of the manual. You can pause the video and do the practice problems on page 4. Otherwise, we'll continue. Okay, so that was pretty simple stuff. Let's build on that and solve the same problem, but with a few real-life examples. A prescription is actually a story that can be set up as a calculation. Say you have worm medicine that the labeling says give 2 tablets per 10 pounds. Your animal weighs 35 pounds. Now let's lay out the calculation. The line in the fraction can be considered the same as the word per. We're going to label it. Remember to keep like comparisons on the same level. On one side, you have 2 tablets per 10 pounds. You need to know how many per 35 pounds. But if you put 35 in the wrong place, your calculation will be incorrect. That is why we label. Now cross multiply the 2 numbers that we have. Divide by the odd. How many tablets do we need? This is a one calculation problem. You only needed to find the quantity. You can pause the video and do the practice problems on page 5. Otherwise, we'll continue. What if the dosing instructions said 20 milligram for every 10 pound and each tablet is 10 milligram? Now you have a 2-step problem. You now must figure out the dosage before you calculate the quantity. We figure out the dosage the same way we did in the last calculation. First, we set up the first problem. We label it, then we fill in what we know. We know we need 20 milligrams per 10 pounds. But we also know that our animal weighs 35 pounds. Now multiply the 2 diagonal numbers and divide by the odd one. And what did you get? We need 70 milligrams. Now that we have that number, we save it. This is the number you carry through to the next step. Now we need to figure out the quantity. Again, set up the problem and label it. We know there are 10 milligrams per tablet. From our last calculation, we know we need 70 milligrams. So we put that there. We need to discover how many tablets that is. How many do we need? 7 again is correct. You can pause the video and do the practice problems on page 6. Then let's continue.
What if the dosing instructions give you a dose per kilogram? Now you have a problem. You must always make sure you're working in the same system. Whether it's pounds, ounces, kilograms, grams, the weight you have must be the same as the weight in the directions. We will cover system conversions next, but for now, these are the 3 steps you need for any drug dosing question. If you start from the top and work your way down, you won't make mistakes. This mnemonic device will help you remember the steps, the 3 safe drug questions. There are several ways to convert back and forth between standard measure, pounds and ounces, and the metric system, grams and kilograms. I've included in your workbook both types of charts for easy reference. You can use these to do the first step of a 3-step drug dosage calculation, and it's quite easy. But for now, let's return to our problem. Since we know the pounds, but the prescription is in kilograms, we need to convert to kilograms so we're working in the same system. Let's look at the conversion calculation chart first. We have the animal's weight in pounds, but we need kilograms. Following the chart's instructions, we take the animal's weight in pounds, which is 35, and divide by 2.2. Round the answer off and you get what? I got 15.9. Let's do the same thing, but this time with the conversion ratio chart. We have pounds, but we need kilograms. We look for the comparison between the 2. We find that on the first line where both are present.
Some ratio blocks contain 3 or more conversions. Don't allow this to confuse you. The first line, the one we're working with, contains grams as well. But since we're not currently working with grams, you can ignore that. Just select the 2 numbers that you need for your calculation.
Now this is a ratio problem just like we've been doing. We set up the problem, we label the components, we put the ratio from the chart on one side, we add what we know on the other.
Now, how do we solve this? Select the diagonal that has two numbers and multiply those two numbers together.
And divide by the odd number. And we get 15.89. And we can round that off to 15.9. Now let's save that number and continue. So now we ask ourselves the safe drug questions. Am I now using the same system? Yes. Now we go to the next step. How many milligrams do I need? We set up the problem. We label the components. We put in the ratio that we know on one side. We add what we want to know on the other. And what's the answer? Now let's save it again. Let's go back to our steps. Are we using the same system? Yes. Do we know how many milligrams we need? Yes. Now if there are 10 milligrams per tablet and we need 70, this one you can do in your head. Okay, so let's do a real-life problem using real medications. You are to give Baytril to a 3-pound red-tailed hawk. We need to gather information. We need the weight of the animal, which we have. It weighs 3 pounds. We also need the drug strength and the dosage for a raptor. So where do we get these numbers? Let's grab the box of Baytril, look at the label to get its strength. It's written two ways. We have a percentage and a ratio. We will talk about drug strength listed in percentages later. But we can get a ratio from this. It says that per milliliter, there are 22.7 milligrams of medication. Now we're going to write these down and save it for our calculation. There's an area for you to do this in your workbook. Now we need to know what the dosage is. The label lists dogs, but we have a bird, so I wouldn't trust this. Every rehabilitator needs a good, reliable, and complete drug book for wildlife or exotics. We will discuss these later, but I grabbed one of mine, and it says to give 10 milligrams per kilogram. So we're going to write that down.
In your workbook, take a moment to work out the calculations. Do each step in order, use the charts to convert to kilograms, and don't forget to label. Pause the video now to give yourself a few minutes to work out the problem, and I'll be right back with the answers. Okay, so what do we get for each step? When converting the system, the 3-pound red-tailed hawk weighs 1.36 kilograms. When calculating the dosage, we need 13.6 milligrams for this bird. And how much medication do we need to measure for the bird? 0.59 milliliter, which can be rounded to 0.6. See, you can do this. More practice problems are available on page 9, and then we'll continue. Now we continue with the metric system. In the United States, the most common use of measure is the U.S. customary units. Although this is the system we've grown up with and the one we are the most familiar with, when we take a close look at it, the U.S. customary system is quite complex and confusing. For example, a yard has 3 feet and a foot has 12 inches. When we look at the measure of volume and weight, it becomes even more confusing. There is no conformity to the units of measure, and odd numbers need to be memorized. In liquid measure, there are 3 teaspoons per tablespoon, 2 tablespoons per liquid ounce, 8 ounces per cup, and a liquid ounce doesn't even equal an ounce. How messed up is that? Welcome to the metric system, a much easier and understandable measure of volume, weight, distance, and even temperature. I've often heard that the metric system is difficult to learn. In reality, it is a simple, organized system based on the number 10. The metric system begins with a unit, a simple measure. These base units are the gram, the liter, and the meter. The gram is used for weight, liter for volume, and the meter for length or distance. Depending on how many base units there are, prefixes are applied in multiples of 10. These are standard no matter what you're measuring. If you have 10 units, you add the prefix deca to the unit, such as 10 grams would be a decagram. Hecto is the prefix of 100 units and kilo for 1,000. With smaller or fractions of a measure, prefixes are applied the same way. 1/10 of a gram would have the prefix deci or decigram. Centi is used for 1/100ths of a unit and milli for 1/1000ths. To put this in perspective, if our monetary system was named like the metric system, our base unit would be the dollar. A $10 bill would be called a decadollar because it equals 10 units. A $100 bill would be a hectodollar. $1,000 would be a kilodollar. For fractions of a dollar, we wouldn't have a dime, but a decadollar. The prefixes deca and deci are often confused, but one way to remember is a dime, which is 1/10 of a dollar, and the prefix deci both have the letter I in the names. A penny would be called a cent-a-dollar. Now there's an easy way to remember the prefix. And we would have a smaller coin, which doesn't exist. That 1,000 of these little suckers would equal a dollar. This coin would be called the millidollar. Those that have problems learning the metric system often go about it the wrong way. We easily can imagine what a pound weighs or how long a foot is, and we try to convert back to standard in our heads. The best way to learn metrics is to forget about the standard system and to begin visualizing what the metric units actually are. For instance, we know that the gram is the base unit of weight, but what is that? What does it feel like? Well, 1 gram weighs the same as one old-fashioned paper clip, so a decagram weighs the same as 10 paper clips. A good point of reference is a nickel. It's worth 5 cents, and it also so happens a nickel weighs exactly 5 grams. For length, the base unit is a meter. Most doorknobs are about 1 meter from the floor. So if you reach your hand out to where you use a doorknob, that's a meter to the floor. The base for volume is the liter. This one you'll use quite often in measuring medication. Most sports bottles are 1 liter. If you pick up a 1 liter bottle of water, you can feel how much it weighs. That is the weight of 1 kilogram. We'll explain why this is shortly. A 1 milliliter syringe holds 1/1000th of a liter. So if you wanted to fill a liter bottle, it would take 1,000 1 ml syringes to do it. It would take 100 10 milliliter syringes to fill a liter bottle. 10 ml can also be called 1 centiliter, but fortunately we don't do that. In the metric system, there are many more levels going up and down to a zillion multiples. But fortunately, in wildlife rehabilitation, we only deal with this range. And of these, the 1,000 multipliers are the ones we use day to day. So it's not as formidable as you might think. But it is important to know this entire range to understand converting from units to kilos, for instance, and in other areas such as drug percentages, which we'll cover later. To easily convert within the metric system, Set up a quick table in this pattern. It's also laid out in your workbook. Using what's called the ladder method will help you remember that the large numbers are to the left and get smaller as we step down the ladder. Converting between units and their prefixes is very simple. As you move each step of the ladder, you move the decimal point in a number the same count of steps in the same direction. Say you have a bottle of feeding supplement and you need to know how many milliliters it contains. Start at the unit you have. In this case, the bottle has 1.5 liters or 1.5. Find the level you want to know, which is milliliters. Count the jumps to that block. We have 1, 2, 3. Now we write that number that we have, which is 1.5 liters, and move the decimal point in that number in the same direction, the same number of jumps. We are moving 3 steps to the right. 1, okay, we ran out of room. If there isn't room in the number, add a 0 where you need it to continue. 2, add another 0. 3. Our 1.5 liters is the same as 1,500 milliliters. You receive a cat-caught baby bunny, and it weighs 30 grams. The medication dosage refers to kilograms. To convert from grams to kilograms, you count how many steps from what you know, which is grams, to what you want to know, kilograms. It is 3 jumps to the left. So if you move your decimal point to the left 3 times, adding zeros if you run out of room, the 30-gram bunny weighs 0.03 kilograms. Even though we rarely use the 10 and 100 levels, as you can see, we need to know that they are there and able to use this ladder system. So how do we remember this range? With mnemonics, just like we learned the 3 steps to safe drug calculations. Now, the one taught in school is King Henry died drinking chocolate milk. I don't like that one. It doesn't include the units, and I can never remember if it's King Henry, King Charles, or King George. It doesn't mean anything to me. I suggest creating one of your own that means something to you. Kind of like kind humans dropping by, donating cash money. And the B stands for base unit. You can also create a funny, memorable picture in your mind, like the one that I use, which is this. Kangaroos, hop, down under. Kangaroos, hop, down under, dodging crocodiles' mouths. As you can see, the metric system is quite easy and it's very organized. It's even more organized when you realize how it was developed. The entire system is based on water and everything intertwines. 1 liter of water at the temperature of freezing weighs 1 kilogram, and the volume it takes up is a cube that is 1 decimeter by 1 decimeter by 1 decimeter, or a cubed decimeter. If you look at the ladder of each measure, 1 liter equals 1 kilogram, which equals 1 cubed decimeter. If we move down 1 level in length, which because it is cubed is actually equal to 3 jumps, and we move the others down the same distance, which are not cubed, so it is 3 true jumps, we discover that 1 milliliter weighs exactly 1 gram and takes up 3 cubic centimeters, which can also be written like this and is abbreviated like this. Now, you may have already known that a milliliter and a cc are equal, but now you know why. And you also know that it weighs 1 gram. This is interesting to know because if you give sub-Q fluids to an animal, it will gain weight by how much you give it. Take a 100-gram opossum. If you give it 5 milliliters of fluid, it will immediately weigh 105 grams, which is a good reason to always weigh an animal before feeding or giving fluids if you're trying to watch its weight progress. A few notes on proper usage so you look as proficient as you now are. Don't put periods in the abbreviations. Don't randomly capitalize. In the 7-step range that we are using, there are no capitals. There are capitals in a few of the ranges that go up to a zillion multiples. And there's always exceptions. The one exception is with liters. Even though it's not capitalized on the chart, it is acceptable to capitalize it to avoid confusion with the number 1. Place a single space between the number and the abbreviation. If you have less than 1 unit, always use a leading zero and a decimal point. Otherwise, the decimal point might be overlooked. You might see liter and meter spelled differently. Both are acceptable. In the US, ER is the common spelling, but the British spell it RE. They are the same measure. Take a moment and do the practice problems on page 12. Being able to accurately measure the functional result of any calculation requires a complete understanding of the basic devices of measure. In this section, we will be covering syringes and scales, as well as the ability to accurately read drug labels and prescriptions. A variety of hypodermic syringes are in common clinical use. In wildlife rehabilitation, we use all different sizes of syringes, from drug and fluid administration to feeding. We use more than most medical professionals. Recognizing the types of syringes and how they measure is a chief safety concern. You can do all the math accurately, but if you measure incorrectly, it doesn't mean anything. Most syringes are calibrated in milliliter or cc's. However, these various capacity syringes contain calibrations that differ from each other, requiring particular care in dosage measurement. When small doses are required, they are most often measured with a 1 milliliter syringe calibrated in hundredths. The long numbered lines are 1/10 of a milliliter. The shorter lines centered between these are 1/20th of a milliliter. And the tiny lines are each 1/100th of a milliliter. For even tinier dosing, smaller syringes are available in 1/2 and even 1/3 cc's. On the 3 milliliter syringe, the longer calibrations identify 0 and each 1/2 and full milliliter. These longer calibrations are numbered 1/2, 1, 1.5, 2, 2.5, and 3. Next, notice the number of calibrations in each milliliter, which is 10, indicating on this syringe each milliliter is calibrated in tenths. There are no 1/100th markings like on the 1 milliliter syringe. So although you can give larger volumes with one injection, your dosing cannot be as exact. Larger syringes are reserved for bolus fluids and feeding. Here the long lines are single milliliters, and in between we can only measure down to 1/20th of a milliliter. You cannot give an accurate, say, 16.17 milliliter dose with this syringe. You can only give 6.2, 6.4, 6.6, 6.8 milliliter. You lose accuracy with larger volumes. When calculating how much of a drug to measure, keep in mind the syringe you're going to be using and do your math down to a usable dose. You need not calculate to the 100th if you're using a syringe that measures in the tenths. The amount used in a 1 milliliter syringe will always be a fraction of a milliliter, written as a decimal. It must always have a leading zero to assure that the decimal point is not overlooked. Test yourself. Picture in your mind where 1/2 milliliter would be. How did you do? How about this one? And this one. And another. Did you get them? If your amount is larger than 1 milliliter, then use a 3 cc syringe to avoid multiple injections. Where would 0.82 be? You cannot measure that. It needs to be rounded to 0.8, which is here. So let's try a couple. Get it? How about this one? And another. How did you do? On the larger syringes, this one happens to be a 12 milliliter. Where would 0.8 be? Did you get it? Try this one. And this one. And one more. How did you do? Look closely at the syringe you're using and double check the measure. Some do not measure in milliliters, or they'll have multiple measures. Look for the ml or cc marking below the scale to avoid errors. For instance, this syringe also measures in teaspoons. Notice that the 3 milliliter syringe on the right contains only one set of calibrations for the metric milliliter cc scale. However, look at the syringe on the left and the odd markings it has. If we roll the syringes over and we see an odd row of calibrations with an M marking, because of the M, these are sometimes confused with milliliters, but it actually stands for minim. This is an old apothecary measure and it isn't useful for much in wildlife rehab. These minim markings can still be found on some 3 and 1 milliliter syringes. If a syringe you're using contains 2 calibrated scales, be particularly careful not to mistake the minim, the M, calibration for metric milliliter calibrations. You know your clinic. If somebody could easily make a mistake with one of these, throw them away. Because rehabilitators often have supplies donated to them, odd syringes can cause real problems. Look at these 3 1 cc syringes. They are the same size. Each holds 1 milliliter or 1 cc, but they are marked completely different. The one on the right is a standard metric syringe, like we've looked at before. This syringe has a clear top. It has the point before the number indicating tenths. The fact that it measures in milliliters or cc's is clearly labeled. These can be used straight from your calculation without worry. The syringe on the left has an orange top. We get a lot of these donated, but look at the numbers. There is no decimal point, and the label says units, not milliliters or cc's. This is an insulin syringe, and it measures units of insulin. If you roll it over, it says U100, meaning there are 100 units of insulin per 1 milliliter. That is why there's no decimal point. It measures 1 unit each line. But because 1 unit equals 1/100th of a milliliter, you can still use it, but only if you can wrap your mind around the fact that the decimal point is missing. If you can't, and numbers get you confused, throw these away. Most 100-unit syringes have an orange top. This can serve as a warning, but don't count on it every time. Now the one in the middle is really messed up. It has a red top. It is the same size as the other 2 syringes and holds 1 cc. Again, it is marked units, but it only goes to 40. Roll this one over and we see there are 40 units of insulin per 1 ml. These can be converted, but quite frankly, I don't even bother. If you grab one of these by accident, an animal could receive over twice the dose it should. These syringes are very dangerous, and when we get them donated, they go right in the trash. Sometimes with very tiny animals, it would be nice to have smaller syringes to more accurately dose down to 1/100ths. Metric syringes are available in 1/2 cc's, but this one is much more common and is often donated. This syringe holds 1/3 the size of a 1cc syringe, and it also has an orange top, so it should be okay, right? There are so many new and funky syringes out today of multiple colors, and even their shapes can vary due to single-dose use safety devices. Don't use color to assume how it measures. Always read the syringe. Okay, back to our tiny syringe. It measures in units, and there are no decimal points. Roll it over, and we read that it measures 100 units of insulin, so each marking is 1/100 of an ml. We can convert this in our head just by placing a decimal point before the numbers, or throw them away if you want, but I find these extremely useful. Just make sure that the amount you measure makes sense. If the amount seems inappropriate, redo your calculations and remeasure. A little extra time can save an animal's life. Not exactly mathematics, but as a useful help, needles are gauged in a standard way. Any gauged needle can come in various lengths, but the gauge indicates its thickness. The larger the number, the finer the needle. In your workbook is a chart of recommended needle gauge sizes according to an animal's body weight, although these sizes may need to be adjusted depending on the viscosity of your medication. More practice problems can be found on page 15 of your manual. Medications are also tools, and understanding how to read the labels and interpret them is essential to accurate dosing. We are looking to fill in part of our earlier equations, which is one side of the ratio. You want to know what amount of drug is in what amount of volume. This would be the drug per volume ratio, and it indicates the drug's strength. And the per is written as a fraction line in our ratio equation. With the drug amikacin, which is an antibiotic, the ratio is written with the word per, making it very easy. It has 50 milligrams of amikacin per 1 milliliter. In the atropine, the ratio is written as a fraction with the slanted line. This contains 15 milligram per 1 milliliter. The ratio for the amikacin would be written as such. Remembering to label, the line represents the word per. The atropine would be written the same way, with the amount, 15 milligrams, on the top and the volume on the bottom. When receiving a new bottle of medication, it makes sense to circle the strength so it's easy to find when it's needed. When I have two similar drugs with different strengths, or if the strength is in very small print or hard to find, I write it on the bottle. Some medications, especially injectables and pills, can have a number listed on the label. Most of the time, this is the strength per 1 ml or per tablet. I wouldn't assume this, though. It can be different. You should still seek out the actual ratio on the label. In this case, the number 50 does represent the strength. Read the labels thoroughly and don't assume that the strength is per a single volume or per ml. This Benadryl has 12.5 milligram, but the volume is per teaspoon. Thankfully, this measure is also labeled as 5 milliliter, but if it were not, you would need to be able to easily convert it for yourself, which you now know how to do from our ratio lessons. Various forms of labeling can be found even with the same drug manufactured by the same company. Baytril, which is a brand name for the drug enrofloxacin, is one of the most common drugs used in wildlife rehabilitation, and it comes in many forms. As you can see, there are many strengths available, and these tablets have the large numbers on the label. The injectable, however, does not. The injectable label doesn't even have an easily found ratio. It uses a percentage instead. The back of the label does list the ratio, but some drugs do not. They merely list a percentage. Ivermectin is a parasite often used to treat mange. This drug is labeled by percentage. Many of these bottles don't list the ratio anywhere. It's up to you to know what that percentage means. Xylazine is another drug that's often listed in percentages. I usually like to show you the math behind a calculation before giving you a shortcut. But this time, I'm going to show you the shortcut first. We're going to go a little more in depth about this when we look at percentages in a little bit, but I don't want to get distracted from understanding working with these medications. For now, the easy way to convert a drug percentage is to first delete the percentage symbol and take that number written exactly as it is. Don't change the decimal point. Multiply this number by 10. This gives you the amount of milligrams per milliliter of that medication. Simple, huh? So the 0.08% ivermectin would be 0.8 milligrams per milliliter. If it's easier for you, you can just slide the decimal point over 1 point to the right. Some drugs are combined drugs and have 2 or more medications together. A good example is vitamin B complex. In a case like this, your prescription orders, the directions you receive from the vet or from your pharmacology book, will guide you on how to proceed. Here we have directions for vitamin B complex administration from 2 different sources. In the first directions, you base the dose only on the thiamine content. In this case, the strength would be 100 milligrams per ml, and the dosing would be 25 milligrams per kilogram. In the second case, you are given the exact amount to measure, which is 0.1 milliliter from the bottle per the weight of the animal in kilograms. If you know your animal's weight in kilograms, then this would be a one calculation problem. You do not need to determine the strength, just the amount. One commonly used combination drug is Bactrim. You may also see this referred to as trisulfamethoprim or shortened to SMTP. In this case, you add the 2 active ingredients together to determine the strength. The 2 drugs are the sulfa and the trimeth. So we add these together and get 240 milligrams of drug. We set up our ratio to look like this. Is that correct? Nope. Read the label. It is per 5 ml, not per 1 ml. A mortar and pestle is an essential tool for wildlife rehabilitators. Because we so often need to treat tiny animals, drugs may need to be diluted. Capsules can be opened and tablets can be crushed so that you're working with a powder. The powder can then be added to liquids such as saline, dextrose, water, or syrup for oral administration of tiny amounts. One thing I really hate to see is someone chopping a pill in 8 pieces or pouring out the powder from a capsule and dividing it into little powder stacks. It's extremely inaccurate, and it looks like you're about to snort a line of Coke. The math of this is quite easy because it's based, again, on our ratio calculation. To dilute pills and capsules, first determine how many milligrams of medication is in 1 capsule or tablet. Put that number here. Next, determine how many milligrams of drug you need per dose. Put that number here. Then estimate what volume you can comfortably give that animal to drink. Put that number here. Cross-multiply, and your answer gives you exactly how many milliliters of fluid to put the powder in. Now label your new medication. You want to label it as a number of milligrams per 1 milliliter. You do this by doing a second calculation. You can keep either side of this equation, it doesn't matter, because they're equal, so eliminate one side. On the opposite side, put the number 1 on the bottom, and cross-multiply again. This gives you the milligrams per milliliter. On the label, write the name of the drug, the new strength, and the date. Also label shake well, because this will need to be shaken each time it's used. Now you have a medication you can use each time or save for the near future, and you don't have to calculate it again. Diluting liquid drugs to a weaker strength is similar, but with one additional step. The first 3 steps are the same. We take the strength of the drug, put that drug strength here. We don't use the per volume in this step yet, but keep it in mind. Next, determine how many milligrams of drug you need per dose. Put that number here. Then estimate what volume you can comfortably give that animal to drink. Put that number here. Cross-multiply and use your answer for the next step. Now take that answer from the last problem and subtract from it that drug volume number I told you to keep in mind. This is the amount on the label after the word per. What you have left is how much liquid you will add to the volume amount. For instance, you have a tiny creature and it needs to get 0.4 milligram of sulfatrimethoprim. You calculate it according to the label and you discover the amount you need to measure out is less than 1/100th of a cc. That's way too small to measure. You decide that 0.03 milliliters is a good amount to give to this animal, so we need to dilute it. So our goal is to make 0.4 milligrams per 0.03 milliliters. We start with our drug strength. Put that drug strength here. We don't use the per volume in this step, but again, keep it in mind. Next, determine how many milligrams of drug you need per dose. We need 0.4 milligram. Then estimate what you want to give, which is 0.03 milliliters. Cross-multiply, and we get 18, which we'll use in the next step. If you add the drug to this amount, you will not get the correct ratio. You must include the volume of drug in the full amount of medication that you're going to make. There are 2 ways to do this, mathematically and mechanically. Mathematically, you need to subtract out the medication volume to find out how much liquid to add. Take your answer. Amount of liquid will make 18 milliliters. Subtract the volume part of the drug strength. In this case, it's 5 milliliter. And subtract. These are the volumes you mix. Mechanically, do your calculation to discover how much volume you will make. Choose a syringe large enough for the full amount you will make. In our example, we will choose a 20 milliliter syringe. Pull 1 measure of the medication, the per volume amount of the strength, which you determined was 5 milliliter. Now fill the syringe with liquid until it reaches the total of how much medication you want to make, which is 18 milliliter. All the calculations that I'm showing you today, including these last few, are fully outlined in your workbook. So if you keep your workbook, you can always refer back to these calculations. When diluting injectables, much care must be taken choosing what liquid to use as the dilutant. It must be sterile and must mix with the drug properly. Sterile water comes in 30 milliliter vials. Sterile saline can be used with some. And propylene glycol is another choice. If you don't know which to use, ask your vet, pharmacist, or consult written material that accompanies the drug. You can't just mix in anything. For example, diazepam is insoluble in water. Propylene glycol, which is a solvent in its clinical injectable form, is appropriate. A prescription, the written directions for how to administer a drug, is also a tool. Carefully following the directions is the most important aspect, and to do that, you need to know how to read the language. Drug abbreviations are broken down into 3 categories: amounts, frequency, and administration. We've already covered amounts. How many times a day a drug is given is written ID, which is Latin for in die. You can remember it as in a day. The abbreviations are shown here with their Latin. To remember these, I think of B as bi, meaning 2, like a bicycle. Q is quad, meaning 4. S is single, and T is tri, or 3. That's easy. SID is virtually unknown to health professionals outside of veterinary medicine, and the vast majority of pharmacists have never seen it used. You may see it, however, although many believe that SID should be eliminated from all veterinary usages. Less frequently, you may see abbreviations that begin with the letter Q. In this case, it doesn't mean the number 4, it means every. Other than the every hour ones, the most common is Q3D or Q72 hours, which is once every 3 days, common in reptile antibiotics. You may also see ones that mean not scheduled. Ad lib means freely as wanted or needed. That does not mean giving it more than recommended each day, though. PRN means as the occasion requires, or if and when needed. Again, you must stay under the maximum daily allowed amount. To effect is usually given in a low to high range, and the dose is increased until the wanted effect is reached. Abbreviations for administration, in alphabetical order, how do you get the drug into the body? IP is interperitoneal or into the peritoneum. IV is in a vein. PO is by mouth. SQ is subcutaneous or under the skin. Scales are essential tools. There are 3 types available that are very reasonably priced. If you care for many different species, such as tiny songbirds to larger mammals, I suggest having all 3. The first 2 types are postal scales and may come in ranges. You can find ones that weigh up to 25 kilograms and others that only go to 5 kilograms. They can vary in how high they go, but what you really want to look for here is the increments. 1 gram increments are best for smaller animals, especially if you're watching for weight loss or gain in a small animal. With the larger, you gain capacity but lose accuracy. It's a trade-off. You should have both. Both of these sell on eBay and Amazon, usually for under $25. Also on various websites, you can find jewelry scales. These are for measuring tiny amounts of gold, and although they only weigh up to 100 grams or so, look at the increment accuracy. You can watch the growth of a baby hummingbird with one of these. I recommend every songbird person has one of these. I have personally had good products and service from 3 places online: eBay, Amazon, and Raven Scales Online. Getting the correct directions for dosing is imperative. Exotic Animal Formulary is available from the NWRA. Plum's Veterinary Drug Handbook is the most comprehensive of all the veterinary drug books that is organized by drug. I go to this book all the time. It is broken down by drug with complete write-ups on how the drug works, drug interactions, and availability. It lists most common exotics and gives different dosing ratios that have been published and approved. If you are only going to get one book, this is the one to get. It's available on Amazon, in print, and there is a Kindle edition, but the print edition is much easier to use. Additional practice problems can be found on page 20 of your manual. We've already touched lightly on percentages in reference to drug strength. Now we want to get a really good understanding of calculating percentages. Percentages are used heavily in 2 critical areas of wildlife rehabilitation: stomach capacities and fluid replacement. Again, I apologize for starting out so elementary, but I want to take you from the very simple to the complex. Once again, I want to begin by using money as an example. Consider $1 as being a whole amount. 1 cent is 1/100th of a dollar. Each cent is 1%. There are 100 of these little puppies in a dollar, and each cent is 1%. A percentage can be written several ways. It can have the percent symbol, or it can be written as a decimal. It can also be written like a ratio. Look familiar? In numbers, it would look like this. You can find the percentage number with an easy calculation that you've already mastered. This is a ratio problem, just like we did earlier. This time, your labels are going to be the whole and the percent or part. The left is your control side, and the bottom whole is always 1/100th. The top is the percent you want to find. On the right, the whole is the number you know. Now you use your calculator to cross multiply. The answer is 16. Why is this important? Well, let's change the problem. You have an infant raccoon that weighs 320 grams. Its stomach capacity is 5% of its body weight. Whether you're determining drug capacity or how much sub-Q fluids to give, always weigh your animals in grams. Remember, 1 milliliter of water weighs 1 gram. Other fluids are close in weight, especially in small amounts. Since food and fluids are almost always measured in milliliters, if you always weigh your animals in grams, capacity is an immediate, easy one-step conversion to milliliters. Now, I understand you could just use a calculator to find a percentage of any number. But I have an important reason to encourage you to learn percentages this way, and that's with hydration. Critical hydration means giving an animal enough fluids in a day to supply its daily needs, in addition to replacing what is missing when the animal arrives. The daily requirement for most animals is between 5 and 10% of their normal body weight. Most stable adults need about 5%, and some animals, such as raptors, will get this amount from their food. Growing babies need more, about 10%. Keep in mind these vary, especially if an animal is losing fluids, such as happens with diarrhea. Placing babies on heating pads without allowing for humidity levels will also cause fluid loss. Calculating the daily fluids needed on a healthy animal can be easily done on a calculator. The problem arises when an animal comes in dehydrated. You receive a baby coyote and it weighs 850 grams. Its eyes are sunken and its skin doesn't snap back when you do a skin turgor test. According to your charts, your best guess is it's suffering from 15% dehydration. Now we want to supply its daily needs, which is 10% because it's a juvenile, plus we want to rehydrate him. Giving him a full 25% of his body weight in one day is going overboard. His little body won't be able to hold that, and his capacity limits us. So we want to rehydrate him over the first 3 days. The following is standard rehydration protocol. On the first day, we give him his daily need plus half of his rehydration need. Half of 15% is 7.5. We supply the remainder over the next 2 days. So on day 2 and day 3, we give him each day his daily need plus 1/4 of his rehydration need. Now herein lies the problem in using the calculator. Most people will use the 850 grams as their calculation number and just multiply by 7.5%. But the animal's proper weight is already down 15% because of the fluid loss. The fluid requirements are based on his normal weight. You need to know what that is and what he really should weigh. As an animal loses hydration, its body weight drops in proportion at a rate of 1 gram per missing milliliter of fluid. An animal that has lost 15% of its body weight now weighs 85% of what he normally would. His normal weight would be 100%. For instance, take our coyote who weighs 850 grams. As you can see by our chart, his normal weight should be 1,000 grams. And you cannot take the 850 and add 15% because 15% of 850 is 127.5, and that just doesn't add up. So how do we find an animal's normal weight? With a ratio calculation. Remember, 100% is always the whole. So what number do we put on top? Well, if it lost 15% of its weight, then 85% is left. Now we fill in the rest. We want to find what the normal, or what 100% of the animal's weight should be. The 850 grams is what we have left. So we put that on top. Cross multiply, and you get the right answer. This was easy numbers to work with, and now you may understand why I want you to get used to working with the ratio calculations, even with percentages. You might wonder why this is so very important. Let's use our coyote to compare the numbers. We will set up a hydration protocol for both weights. When using the 850 grams, the first day he would receive 10% plus half of the 15% he's missing. So day 1, he gets almost 150 milliliters of fluid. Day 2, he would get his 10% daily plus 1/4 what he's missing. And we repeat that on the third day. In 3 days, he gets 382 milliliters of fluid. When calculated by the proper weight, the first day he gets 10% plus 7.5%, and he gets 175 milliliters of fluid. Day 2, he would get his 10% plus 1/4 what he's missing. And we repeat that again on the third day. In 3 days, he gets 450 milliliters of fluid. That's almost 65 milliliters short. That's equal to you not giving him any rehydration fluid the first day at all. That's a huge difference. So how do we determine how to set up the ratio? How do we determine what percentage to put in the calculation above the 100? How do we determine where to put the animal's weight? Don't memorize this setup. That's going to quickly be forgotten. Understand it, and you will always know how to set it up. Let's say an animal is 12% dehydrated. You want what is remaining. Take that estimate and subtract it from 100. You now have the animal's percentage of the normal body weight. With 12% dehydration, the animal is currently at 88% of its normal weight. Again, from the very beginning, I explained that this is why it's important to label. Where do we put these numbers? Remember, the 100 is always the whole amount of the percentage side. This number above the 100 is what's left after you subtract the dehydration. With 12% dehydration, the normal is 88%. So let's put that there. The animal's current weight is not the whole, so it doesn't go on the bottom. It's equal to the percentage we have remaining, so that goes here. Now you do your math, your ratio math. You cross multiply and divide by the single number. And it works with all numbers and all levels of dehydration. Let's try a couple. We have a bunny that weighs 130 grams and it has 10% dehydration. 100 is the whole. So what number do we put on top? Well, if it lost 10% of its weight, then 90% is left. Where do we put the animal's current weight? It goes on top. Cross multiply, and you get the animal's normal weight. We have an owl with 5% dehydration, and it currently weighs 1,750 grams. So what number do we put on top? Well, if it lost 5% of its weight, then 95% is left. Where do we put the 1,750? It goes on top. Because it's not the whole, it's a percentage of what the whole would be, which is what his normal weight would be. Now cross multiply and get your answer. So how do you determine how dehydrated an animal is? A blood test for a packed cell volume is the most accurate, but our chart will get you close enough. And there's a copy of our chart in your workbook. On page 23 of your workbook, you have an adult squirrel that weighs 500 grams and is suffering from 5% dehydration. Using this protocol, take a few minutes and calculate a rehydration therapy program for this squirrel. While we have percentages fresh in our minds, I'd like to return to the drug strengths listed by percentage. Remember, I gave the shortcut to delete the percentage symbol and multiply the number by 10. This gives you the milligram per milliliter drug strength. Well, here's how calculating drug percentages works. This is where everything you've learned so far comes together. First, we learned that 1 milliliter of water weighs 1 gram. That means that 100 milliliters of water weighs 100 grams. This is important since we're working in percentages and the whole is always 100. As a ratio, this would also be written like this. So a medication listed as 1% would be written like this. But this is where most people make their mistake. This is grams per milliliter. We want milligrams per milliliter. So we need to convert the top number from grams to milligrams. And we do that using our metric system ladder method. We count the steps from grams to milligrams. 1, 2, 3 steps to the right, and move the decimal point the same number of moves in the same direction. And as we see, that 1 gram is the same as 1,000 milligrams. So a 1% drug, which is 1 gram per 100 milliliters, is exactly the same as 1,000 milligrams per 100 milliliters. But this is per 100 milliliters. We want to know what it is per milliliter. You can either reduce the numbers by removing the same number of right end zeros on the top and the bottom, or if you need to practice, set up your ratio problem and cross multiply to get the answer. So we're almost at the end of our session, but I'd like to quickly go over one more thing that I'm often told is confusing for some rehabilitators, and that is calculating how many calories an animal needs.
So how do you know how many calories an animal needs? Well, we have a formula for that. Calculate the animal's weight in kilograms to the power of 0.75. Multiply that times his species constant times the stress factor. I realize it looks complicated, but we're going to break it down step by step and make it very simple. First part, weigh the animals in kilogram. In very small animals or in scales that only do grams, weigh them in grams and divide the number of grams by 1,000. So we have a squirrel that weighs 50 grams. Divide 50 by 1,000 and that equals 0.05. There are 2 ways to find the 0.75 power. Some calculators have that function and you can just input that. On a scientific calculator, just enter 0.5, then the YX key, then 0.75, and finally the equals key. Your result is 0.105. If your calculator doesn't have this function, then we need to determine the results the second way. This is done by weight times weight times weight times square root times square root. Simply, the weight in kilograms, which is 0.05 times 0.05 times 0.05, hit your equal key, and then hit your square root key twice. The result will be 0.105. For those who are mathematically inclined and want to understand how this works, to the power of 0.75 is the same thing as to the power of 3/4 as a fraction. A fractional power relates to the expression of the power in numerator and denominator form. You have 3/4 for the 0.75 decimal. If you present the problem as a fraction, it would look like this. And it's written like this. You take the weight to the third power, then cube the root, which is what we just did on the calculator. Okay, enough of that. Now back to our original calculation to find the daily caloric needs for this baby squirrel. So, the squirrel weighs 0.05 kilograms to the power of 0.75, which is 0.105. Now we multiply this by the species constant. These are standardized into groups depending on the animal's metabolism. In marsupials, the metabolic constant is 49. In placental mammals, it is 70. Your non-passerine birds, which are your birds that are not songbirds, this includes eagles, grouse, gulls, game birds, ducks, it's 78. Passerines, which are your songbirds, jays, thrushes, flycatchers, even crows, are 129. Our squirrel is a mammal and it's not a marsupial. It's a placental mammal, so our constant is 70. So we multiply the 0.05 times 70 and the result is 7.35. This number equates the amount of calories that that animal needs just to maintain respiration and for its organs to work in a thermal neutral environment. It doesn't account for growth, healing, movement, or its need to keep itself warm or cool. This is called its metabolic base. As you can see, the constants are different for various types of species. A 50-gram opossum won't need near the calories that a 50-gram songbird needs because their metabolism is much higher. But any animal needs more than its metabolic base depending on what's going on in its life. A growing baby will need more calories than an adult. An injured animal will need more calories than a healthy animal, so it has the energy to heal. This is where the stress factor comes in. A healthy animal needs twice its metabolic rate to have the energy it needs, so its stress factor is 2. An adult recovering from injury or illness needs even more energy. That stress factor is 3. A healthy growing baby needs twice that of a healthy adult to allow energy for growth. The stress factor is 4. A growing baby recovering from injury or illness needs even more than a healthy baby, and that stress factor is 5. If we are calculating for our baby squirrel above, we can see it's not healthy. This is a sick baby. So we are going to times our base metabolic rate by 5. The result is how many calories this baby squirrel needs in 24 hours. 36.75 calories a day. Your handout for this lesson contains common foods often used in rehabilitation and the calorie content of those foods. Other useful places to get this information are calorieking.com, which has a nifty search engine. When you find the food you're looking for, you can input the serving size in ounces and even grams. The calorie amount is calculated for you, as well as the amount of carbs, fat, protein, and calcium. The USDA has food composition charts that are quite extensive. You can also input the serving size and calories are calculated, as well as vitamins, minerals, sugars, etc. These sites are listed in your handout.
I really hope you enjoyed this time learning about medical math. I love math, and I really enjoyed sharing this with you. Thank you.